Hello, it's Mr. Potensky, and we are looking at problem number 9. So this one is a little bit more intricate than some of the other ones we've done today. We were asked, the cube has a volume of 340 cubic inches, and then we're asked to approximate the length d of the diagonal to the nearest whole number. So that's the diagonal going from the back top to the lower front. Um, and so we need to think about this. And so before we go any further, I want you to brainstorm in your class, or if you're doing it on your own, um, brainstorm some of the properties you know about cubes and squares. So hopefully you pause the video and we will be rejoining each other soon. So now that we are back, what did you come up with? You may have come up with some ideas that you know the um, the diagonals of um, of a square. So the diagonal of a square is the side length times the square root of 2. So we know that as a property. And so um, uh, then also um, with triangles and with our right triangles, we can use the Pythagorean theorem. So things to know here is we can set up a relationship. So, or several relationships, I should say. So I'm going to lay out these triangles flat. So we know we have this cube, and to find the volume of a cube, it is going to be the side length multiplied by the side length multiplied by the side length, or s cubed, is going to equal 340 cubic inches. Okay, so we could calculate the side length, and if you wanted to do that, you could do that in Desmos. Okay, so let's go ahead and open that up. So when we have that open, um, like we have that relationship there that s to the third is equal to 340, but that doesn't tell us what s is equal. So to undo the cubed root, or the cube, we need to take it a cube root. So s is equal to the cube root, so we can do CB RT, similar to the SQ RT for square root. So the cubic root of 340, and we could find that value of s. But that, I mean, that if we just go straight to that and then we use those numbers right away, that's going to make our whole process more difficult. So um, that's just something good to know. Okay, so we have this relationship, and then we're going to draw out. We have one triangle here. Okay, and it's a right triangle where we're looking. So I'm looking at this one right here because we need to find this length. We know what that length is, but we need to find this other side length to be able to find the length of D. So we have a right triangle with with our leg length S. Okay, so that's an S, not a 5. And then we're going to go ahead and label this L. Okay, so we could say that S squared plus S squared is equal to L squared. Okay, so we can make that relationship out of this triangle right there. We also have another triangle. It's a little bit bigger. So it has, and we're looking at this one. So it has a side length or a leg length of S, and then also the leg length of L. So we had to go through and it's lowercase l. Okay, and so we can make the relationship that S squared plus L squared is equal to D squared. So now we're really getting into some things here and trying to figure out what all we know. So doing this, now we can go through and we know what L squared is equal to. It's S squared plus S squared. So now we have S squared plus S squared plus S squared is equal to D squared. And that's 3S squared is equal to D squared. And then from there, to get D by itself, we can rewrite that. D is equal to the square root of 3S squared. And we've already calculated what S is, but it sure beats using that 6.979, etc., and writing that out every time. That's why we do things with algebra, is using our variables makes it simpler. So now all I have to do is actually use the S because I have it as D is related to S. So I don't have to actually even do the intermediate step of figuring out what L squared is. So we can do this, and we're going to do SQRT of 3 times S squared. So because of how we set this up, we get it straight from, we pulled the value that we calculated here and it puts it in there and substitutes it in for us. So it asks us to round to the nearest whole number, which is D is approximately 12 units. So that is our answer. And when we're asked to justify our answer, we made relationships. We know this because of the relationships of diagonals.